Dear students of third year Mechanical Engineering Department, myself Rajesh Kumar Oja. In this lecture, multi-degree of freedom system is described or discussed. Mainly 2 degree of freedom system will be covered. Important terms are discussed as follows. First, system with 2 degree of freedom. Important. This system with 2 degree of freedom. This topic that belongs to vibration engineering subjects. Some of the important terms which are discussed. First, multi-degree of freedom. Multi-degree of freedom. The motion of the system is described by more than one coordinate called multi-degree of freedom. It can be written as NDOF system, where N stands for number of coordinates. Hence, for 2 degree of freedom requires 2 independent coordinates to define its motion. These independent coordinates are also called principal or natural coordinates. Next, there is need to compare with single degree of freedom. In single degree of freedom, when the system is subjected to a certain excitation, the occurring or emanating motion is described as natural vibration. It means that the system vibrates at the system natural frequency. But NDOF system has n number of natural frequencies, whereas single degree of freedom has single system natural frequency. N natural frequency of the system has n number of displacement configurations called principal or natural modes of vibrations. Depending on initial condition, the system can vibrating any of these modes. Each mode corresponds a unique frequency referred as natural frequency. So there are as many natural frequency as there are principal or natural modes. If the principal mode of vibration, the amplitude of one of the masses is considered unity, then the mode of vibration is called normal mode of vibration, and normal modes are a special case of vibration. Random vibration is not a normal mode vibration. However, any general vibration of the system can be represented by the sum of its normal modes of vibration with suitable amplitudes. This shows the importance of a study of normal mode of vibration. Now take an example, normal mode. Of vibration already discussed. Take an example to understand the two degree of freedom system. So here this is the 2 degree of freedom system. Two degree of freedom system with a stiffness that is a 2 mass, 1 mass having m and another one is 2m. There is natural coordinates x1 and x2 or displacement principal coordinate, sometimes it is also called. And the free body diagram of this system can be drawn here. K x1, K x2 minus x1, 2m, kx2, kx2 minus x1. This is free body figure. This is the free body diagram. The mathematical formulation for a 2 degree of freedom consists of 2 simultaneously ordinary differential equations. The equation of motion for the above systems can be written. Let this free body diagram A and B. So for free body diagram A, we can write equation of motions m x1 double dot minus k x1 plus k x2 minus x1 is equal to 0. Upon simplifying, we can write mx1 double dot plus 2kx1 minus kx2 is equal to 0, and this is the first equation. For figure B, we can write 2m x2 double dot plus kx2 plus kx2 minus x1 is equal to 0. Upon simplifying, we can write 2m x2 double dot plus 2k x2 minus kx1 is equal to 0. That is second equation. For normal mode of oscillation, each mode experiences a harmonic motion of the same frequency passing through the equilibrium position simultaneously. So we can write x1 is equal to a1 sine omega t and x2 is equal to a2 sine omega t. Now putting these values x1 x2 in equation first, x1 x2 in equation first, this x1 x2 value in equation first, we can find minus putting x1 and x2 equation third. In equation 1, we find or we get minus ma1 omega square sine omega t plus 2k a1 sine omega t minus k a2 sine omega t is equal to 0, or 2k minus m omega square a1 minus k a2 is equal to 0. This one is fourth equation. Putting again equation third in equation 2, we will get again putting the values of x1 and x2 from equation third in equation second, we get these values, it will be put in these equations, and we get minus 2m a2 omega square sine omega t plus 2k a2 sine omega t minus k a1 sine omega t is equal to 0, or 2k minus 2m omega square a2 minus k a1 is equal to 0. This is the fifth equation. Fourth and fifth equations can be expressed in the matrix form. That can be written 2k minus m omega square minus k 2k minus 2m omega square a1 a2 is equal to 0 0. For this is the determinant. Sorry, this is the equations that is kept in the matrix form. For any value of a1 and a2, the determinant should be equal to 0. Let omega square is equal to lambda. Upon solving this determinant, we will get the characteristic equations, and that will be lambda square minus 3 by 2 sorry, 3k by m lambda plus 3 by 2 k by m square is equal to 0. This is the sixth equation, and now we have seventh equation. Now we have seventh equations. This is the sixth equation, and this is the seventh equation. So further we can go for this is the equations. It is characteristic equations. It is quadratic equation, and here there are two roots, lambda 1 and lambda 2 can be found. Lambda 1 is equal to 0.634 k by m, and lambda 2 is equal to we can say so 2.366 k by m. So lambda 1 and lambda 2 can be calculated. There is the quadratic equations you can solve very well, you know. You can solve easily. So from here we can find out natural frequency omega 1 is equal to under root lambda 1, and we will get 0.634 k by m. And omega 2 you will get lambda 2 is equal to 2.366 k by m. From equations fourth and fifth, from equation fourth and fifth, the ratio of amplitudes are obtained. So we can write A1 by A2 is equal to k by 2k omega square m is equal to 2k minus 2 omega square m by k. That is considered eighth equations. This is the eighth equation. Eighth equation has two equations. One we can write A1 by A2 is equal to k by 2k minus omega square m, or another equation can be A1 by A2 is equal to 2k minus 2 omega square m by k. So out of these two equations, one equations can be used to find out the amplitude ratio. Corresponding to the first natural frequency, the amplitude ratio corresponding to the first natural frequency, the system omega 1 square is equal to 0.634 k by m. Putting these values here, A1 by A2 is equal to k by 2k minus omega 1 square m is equal to, we can write k numerator and denominator divided by k. We will get 1 Here we will get 2 minus 0.634, and that gives 0.732 or 0.731. What we have done, again I am going to repeat the same. From equation 4 and 5th, the ratio of amplitudes are obtained. A1 by A2 is equal to K by 2K minus omega square M is equal to 2K minus 2 omega square M by K. That is the 8th equations, and it has two equations. A1 by A2 can be calculated by using this or this. So A1 by A2 is equal to K by 2K minus omega square M, or A1 by A2 is equal to 2K minus 2 omega square M upon K. So the amplitude ratio corresponding to the first natural frequency of the system when omega is 1 square is equal to 0.634 K by M, the A1 by A2, that is equal to 0.731 corresponding to the first natural frequency. Now corresponding to the second natural frequency, the amplitude ratio can be written A1 by A2 to here second natural frequency, amplitude ratio corresponding to the second natural frequency, that is omega 2 square is equal to 2.366 K by M. We will get amplitude ratio corresponding to the second natural frequency, will get K by 2K minus omega 2 square M, and we will get, upon solving, we will get minus 2.73. So from here it clears the amplitude ratio we will got, and the amplitude ratio we found by using equation 8. So not their absolute values, which are arbitrary. If one of the amplitude of one of the masses is considered unity, it is said to be that the amplitude ratio is normalized to that number. The two normal modes of the system are as follows. So we can write phi 1x is equal to 0.7311, phi 2x is equal to minus 2.731 1. This is the two normal mode of the system. They are as normal mode vibrations can be expressed as x is equal to A1 phi 1x sine omega 1t plus psi 1 plus A2 pi 2x sine omega 2t plus psi 2. The normal mode of the system can be shown graphically. When omega 1 square is equal to 0.634 K by M 0.731 1 when the natural frequency omega 2 square is equal to 2.366 K by M minus 2.73 and this one is 1. Here that is normal mode of the system, that is normal modes of the system. Normal mode of the modes of the system is graphically shown, and here first for first normal mode both of the masses move in the same direction, and here both of for second normal mode both of the masses move in opposition or in opposite directions. So I think that all of you people are understand, or now you are able to find out natural frequencies and normal mode of 2 degree of freedom system. So there is one of the assignment. This is the assignment number 1 of this lecture. Assignment number 1 of these lectures. This is the assignment number 1. Please try to solve these problems. If you will face any problems to solve these examples, you may ask questions by using my email ID or my WhatsApp number. Thank you.